Greetings and welcome, ladies and gentlemen. We're looking at areas under the curve, talking about integral calculus, finding the definite integral. And we're going to look at this problem and do it kind of generically, not using the definition of an integral to do this. But I just want to point out some of the facts that we know. If I was to do this, a would equal 0, b would equal 2, my function would equal x plus 1. What would delta x be for us?
2 over.
That would have been right, 2 minus 0 over n, right? Or 2 over n. And then what would x sub I equal?
2
sub I over n. It would be 2I over n. 2 sub I. No, 2I.
It's just 2I.
Let's see. So x sub I is equal to a plus I times delta x, right? A is 0 in this case, plus I times delta x, so I times 2 over n. And so x sub I is just 2I over n, twin. And actually, on the last problem we had, problem 15, a was not equal to 0. And perhaps you noticed some difficulties in the fact that whenever you'd square, you'd end up having to expand a binomial, and it just got ugly, right? So I'll teach you a trick to just say, always let a be 0. I'll show you how you can do that later.
Wasn't that example 2 where you do
Yep. If a is always 0, you can always then just have a monomial term for your x sub I, and it makes things easier. So if I was to do this the long way, I would have then had the limit as n goes to infinity of the sum as I equals 1 to n of f of x, which is x plus 1. So that would have been f of x sub I is what I'm plugging in here. So that would have been 2I over n plus 1 multiplied by delta x, and then dx is what I'd end up doing. So notice that I replaced just the x portion of f of x with x of I.
Why did you put the dx at the end?
Dx is part of the notation of... oh, actually, wait. You're right. Dx shouldn't be there. That's only in the integral notation that it would show up. Good call. Thank you. So, however, I didn't need you to do this, but I figured I might as well relate it to all of this just so you're aware. If I just wanted to straight find the area of this, you can do area addition postulate, where you break this up into 2 smaller parts. So we can find the area of this triangle and the area of this rectangle. Right, so this area is 2 because it's 1 by 2. The area of this triangle, 2 by 2 divided by 2. And that ends up also equaling 2 because the area of a triangle is 1/2 the base times the height. Area of the rectangle is length times width. And you end up getting 2 and 2 for both of those. Add them up, you get 4. So that's what you end up getting. But that is actually the same thing we would get if we ended up doing it this way. And actually, yeah, never mind. We're good. We're good. So there's problem 10. At least get our feet wet here a little bit. Let's consider problem 13. Oddly enough, having the same answer. Let's see. Here we go.
So how's the same shape? So what time does class end again?
Eventually. I have no idea. So much later that the old narrator got tired of waiting and they had to hire a new one. So yeah, it ends up being a linear function here as well. So let's label what we've got. I've got a... Oh, wait, 13. A is equal to 1. Okay. A equals 1. B equals 3. F of x is equal to x. And in this case, a equaling 1, or a non-zero value, isn't terrible for us because this function's linear. All right? once I have to like square x sub I or cube x sub I, that's when it would be a pain. So let's see what happens here. So let's see, I can then find delta x. How would I find delta x? 3 minus 1 over n, so 2 over n. X sub I is going to equal a, which is 1, plus I times delta x, right? So x sub I is equal to 1 plus 2I over n. All right? So I've got all of my pertinent information here, right? So let's find the definite integral. So this is going to equal the limit as n goes to infinity of the sum of I equals 1 to n of f of x sub I. So f of x is just x. I'm not squaring it, I'm not cubing it, I'm not subtracting something, I'm not multiplying it. So in this case it's just x sub I. So 1 plus 2I over n. And I multiply by delta x, which is 2 over n. Right? So let's keep going. Moving right along. So this will be the limit of the sigma of, I guess we could multiply this out, perhaps. So this would be 2 over n plus 4I over n squared. I don't know, does it benefit us to multiply it out? Or should I keep these separate?
Yeah, you know what I did
I could
was,
break it into 2 sigmas, couldn't I?
Yeah, that's how I did it.
Is that what you did?
It's as long as heck, but
Yeah, I might break this into the sum of this and times the sum of that, which will actually end up equaling the same thing. So 1 plus 2I over n.
no, that's not what we did.
No?
No.
Did
We
you guys
solved
get it
them
a different
both
way?
For, starting at 0. Right.
You did a equals 0? Or
We did, we solved for...
oh, you had I starting at 0?
Yeah.
Really?
Yeah.
Hmm.
And then, subtracted from I going to 1. Or,
So if you have I start at 0, then don't these have to be n plus 1s? No?
no, not, but,
I'm not entirely sure what you're referring to.
we did...
Yeah, you didn't have to do it on this one, though. Right? So let's see. But yeah, it is easier when these are linear terms, though, I suppose. So I don't know. I might try this double sigma one. What do you guys think? And this is the way you used and it worked?
I don't know. What I did was
Or did you multiply it out?
Wait, what's the term?
Because it just might be tricky finding the pattern
I
in
did
these.
definite integral of 0 to 3 and 0 to 1, then subtract the definite integral of 0 to 1 from 0 to 3.
Right, yeah. So that's what you ended up doing, the trick that we'll do later, having a be 0
For both.
and doing 2 separate ones. Well, let's see what happens if I multiply this out then. Why not? Let's just... because all this is going to be is, can I find a pattern that it will match with? So let's see what we get. So this will be sigma of 2n plus 2I over n, where I'm adding all of those up. So that would end up equaling the limit of, and we'll have...
4I over n squared.
Oh, thank you. 4I over n squared. I had that one earlier too, and then I didn't write it that time, sadly. 4I over n squared. So I'm adding 2n repeatedly. So one of the patterns is going to be 2 over n plus 2 over n plus 2 over n plus ... plus 2 over n. And then the other one would be this 4in squared. So when I is 1, It'll be 4 over n squared plus 4 over, 4 times, that I didn't end up getting squared, did it? So 4 times 2 over n squared plus 4 times 3 over n squared plus ... 4 times n over n squared, right? That's what we end up getting.
You know what, I think that the first one, the 2 over n plus 2 over n plus 2 over n, and so on, I think it's just going to be equal to 1, because if n was equal to 1, then it would be 2 over 1, which is 2. If n was equal to, it would be 2 over 2 plus 2 over 2, which is 2. If n was equal to 3, it would be 2 thirds plus 2 thirds plus 2 thirds, which is 6 thirds, which is 2.
Well, I've got, how many of these do I have, though?
What I'm saying is that no matter what n is, the sum of all those numbers is going to be
Just 1?
2.
I think, yeah, okay, that's what I was going to say. I was going to say it's going to equal 2. Because I've got n many of those, right?
But you're dividing them by n.
So instead of repeatedly adding n many times,
You could divide by
that's the same as n times 2 over n, right?
which is just
Which will end up just equaling 2.
20.
Plus, this one, what could I do? Factor out of 4 over n squared. So yeah, I definitely think there's more than one way to do this, but... And then I'll have
Yeah,
1 plus
wish
2
I
plus 3 plus ...
Kind of wish I knew about that earlier.
plus n, right? Close parentheses there. Let's see, adjusting my earpiece. And now this is a pattern, right? So this is the limit of, this is just 2 plus 4 over n squared times, and now I look up this pattern, and I believe that ends up being n, well, I guess I'll just write it
N
this way,
times n plus 1 all
all over 2.
over 2.
Okay.
Cancel out 2s, cancel out n.
So yeah, this n cancels out with one of those, this 2 cancels out with a 4, leaving 2.
Oh.
So this will be the limit of 2 plus 2, and I'll distribute this out, 2n plus 2, all over n, right?
Remember, are you going to be posting this video online?
Yep.
Okay.
Plus, and now for this
So
fraction,
that's just 4 plus 2 over n. 2n over n.
2n over n plus 2 over n, all over n. And actually, I could break this into 2 separate limits now, but I don't think it'll matter. So this will be 2 plus 2 over n, all over 1. And what do we have going on here when I take the limit?
It's finally just 2 plus 2 because that's equal to 0.
There we go. And 2 plus 2 is 4. Okay. So yeah, so this little, some of the factoring and work there is definitely a little bit intriguing. I think there's definitely multiple ways of doing this. The trick that I'm going to show you to set up for the next one will actually have a always be 0, and it'll make things a little simpler. In this case, it didn't matter though. Did anyone have a different technique for this setup here?
What you could have done was just simplify the 2n over n into 2 and then not have to divide by anything. I would have had 2 over n.
You would have simplified this,
No, your last step.
my last step.
2n over n.
Yeah, it's
You
just 2.
simplify that to 2 and then you would
Yep.
have had to divide. And you would have had
Well, this over this? Oh, if I... Well, you can't quite just cancel out the n's. It would be 2 plus 2n over n plus 2 over n.
Yeah.
And then, yeah.
2.
Yep, you could have done that as well. That's fine. And then it'd still be 2 plus 2 plus 0. Yep, so definitely multiple approaches. Because this one's linear, it does simplify a little bit differently. But yeah, so yeah, some of the trick is, I think, in just trying to figure out the ways to factor it. This is an interesting little simplification there. I don't know what I'd recommend for you guys as far as another way to do that, but that's the way I spot it. Let's look at setting up problem 15, because this one just ends up being ugly, if I recall. I think it's possible, just ugly.
Number 15 was absolutely disgusting.
That was
I think I have like a 3
So-
Yeah, if we continue using torture to get information out of terrorists, we should just make them use this problem instead of waterboarding them.
So this is the situation I have. I'm looking for the area under the curve from 1 to 5 of 2x cubed. Okay? Now it turns out I can also find... Actually, let me draw a picture of one. Well, no, I'll do that later. It turns out that will be the same as the area from 0 to 5 of 2x cubed dx minus the area from 0 to 1 of 2x cubed dx. All right. Now I don't know exactly what this curve looks like, but let me draw a possible picture. So this is kind of what we got going on. Imagine the curve looks like this. I don't know. Something like that. So this finds the area from 1 to 5 is what we're looking for, right? So here's the area we're looking for. Here, this finds the area from 0 to 5. And this finds the area from 0 to 1. And if I subtract this area from that, I'll get the area that I wanted. Does that make sense? Similar to when we were doing areas under the curve for normal distribution, we were doing that. So that's the trick, is if you break this into two separate problems, notice that A equals 0 in both of these cases, which is awesomeness, because then you end up not having to cube a binomial a whole bunch, which would be really, really nice.
That's the way that I did it.
Yeah.
I tried keeping binomial.
Yep. So that's the trick. So it's actually easier to do two separate problems than to do one problem, just because of all the really ugly factoring you'd have to do otherwise.
It's more right.
I don't know. I'd
It
be
involves
interested in
more
seeing a
steps,
side-by-side.
but each step doesn't hurt as much as the alternative.
So it's like, would you rather get punched by the Incredible Hulk once, or just like poked by the Flash infinitely many times? I wonder if he'd be really fast at poking people. Doesn't hurt as much, Flash.
Yeah,
Right.
I wonder what it would be like if Barney had to be subjected to slaps giving by the Flash.
Yeah, that'd be interesting, yeah. A less force, but a lot of them. So anyways, so I won't do this entire problem using that technique, but we will see some in today's lesson doing that as well, so that'll be good. But anyways, all right, internet friends, have fun finding those areas under the curve.